everybody. So today we are going to discuss last chapter of this syllabus, class 12 syllabus, and the chapter that which we are going to discuss is semiconductor devices or electronics. So this is the very basic chapter, for studying electronics. All right. So first, I'm not going to do a detailed introduction part because many topic has been deleted from this chapter. So therefore, what I would like to tell you now here is, first I would like to define what exactly what is basically mean by electronic devices. All right, and then what all we are going to study in this chapter, right? Normally I used to do a detailed introduction about this chapter. However, since the many topic has been deleted, transistor has been deleted, and Zener diode has been deleted, and then digital electronic has been deleted. So many topic has been deleted from this chapter. Now this chapter is become very small chapter. So I want to do much on introduction part. All right. So first, what do you mean by electronic devices? All right. And what is the basic building block of an electronic devices? All right. So if I ask you, what is the electronic devices? Electronic devices, these days we see electronic devices anywhere, right? Your computer is electronic device, your simple calculator is electronic device, your mobile is electronic device. All these devices are electronic devices. So these days electronic device becomes very close and we see everywhere around us. So what exactly mean by electronic device? What exactly electronic device does? All right. So the basic building block of all the electronic circuit is these devices allow a controlled flow of electrons. That means current, right? So this device has the full control over the flow of current in a particular device. All right. So basically, in an electronic device, the currents, the informations are in the form of current. All right, informations are in the form of flow of electrons. Right. So the particular device has a full control over the flow of that particular information, and that is what we call as electronic device. All right. So now in this chapter, what we are going to study is we are going to study the basic of those electronic devices. So that is what we call as a semiconductor. So semiconductor. So normally we divide things every metals into three parts: semiconductor, conductor, and insulator. So this part, the semiconductor, is the basic, the foundation for electronic devices, and we will learn how semiconductor is the foundation or the basic building for electronic devices, right? That we will study later, right? All right. So this is what we are going to study, and then we are going to study the types of semiconductors and pure semiconductor and impure semiconductor, that is extrinsic semiconductor, intrinsic semiconductors, and then we are going to study a diode, PN junction diodes. Then we will study an application of diodes. And then at last we are going to study a photoelectronic device, optoelectronic device. So these parts are the portions or the topic which we are going to cover in this chapter. All right. So first, before I start electronic device, right? So first let me divide material into three parts. So basically, we divide every materials that we find is divided into three parts based on its resistivities. All right. So therefore, semiconductor comes between the metals and insulators. The metals is what we call as good conductors, having a very low resistivities, and the insulators are what we call as bad conductors, which doesn't allow current to flow, having a very high resistivity. Semiconductor comes between these two materials, right? That is metals and insulators, right? So semiconductor having this is a resistivity 10 to the power -5 to 10 to the power 6 ohm meters, and this is conductivity, right? So now basically we divide a semiconductor into two parts. That is elemental semiconductors and compound semiconductors. Elemental semiconductors are the semiconductors that we find in our natural, right? That is silicon and germanium are what we call as elemental semiconductors. The compound semiconductors are made up of few elements, that is cadmiums, sulfides, germanium arsenide. These are the, and within that we divide these into organic and inorganic semiconductors. So these things are the how we divide semiconductors, right, based on the elementals and the compound semiconductors. All right. So now we will go into semiconductors. Before we get into semiconductors, what I am going to do is I am going to discuss one very important theory that you might study this in chemistry, right? Band energy theory, right? So we will study this theory and then try to understand what we call as valence electrons and conduction bands. Valence band and conduction. How valence bands and conduction bands are formed in a semiconductor device or any metals, any devices, right? Any materials, right? So this is what we have. Normally we say that silicon. Let's talk about silicon, right? We have silicon having electrons. Number of electron in a silicon is what we call as 14, right? So we have a configuration, that is the arrangement of electron around the nucleus, right? So the arrangement of electron is what we call as, this is how we go, right? 1s2, 1s2, 2s2, 2p6, and then 3s2 and 3p2, right? This is the electronic configurations, right? This is an electronic configuration of silicons. Silicon atom. We talk about silicon atom, right? So when it is if I have a silicon atom, this is the electronic configurations. So the last shell, outermost shell is, this is an outermost shell, right? This is an outermost shell. So outermost shell having 4 electrons. Outermost shell having 4 electrons. Outermost shell having 4 electrons. Alright. One more example I would like to give you is a germanium. So germanium having 32. That is 1s2 and 2s2, 2p6. And then 3s2, 3p6, 4s2, then 4p2. So again in germaniums, outermost shell having 4 electrons, right? Outermost shell having 4 electrons. This is we talk about atom, in an atoms. If I have one single silicon atom, this is how configuration goes on. If I have one germanium atom, this is how configuration goes on, right? Now if I have crystals, right? If I have a crystals, right, that means it is the network of so many silicon atoms. It is a network of so many silicon atoms. One silicon atoms combined with another silicon atoms, right? So the bonding will take place. So in such a case, what happens is that this is what we call as a band energy theory, right? So basically we say that this is how an electrons, right? This is 3s2 and this is an 3s. This is 2. This is 2, right? So 2 electrons. This is this is for when we find individual atom. If I have individual atom, this is how it goes, right? 2 is the number of electrons, n is number of atoms. If I have so many individual atoms, right? If I have an n number of individual silicon atoms, and the outermost shell is going to be 2n, and this is what we have. And P has 6 vacancy, right? 6. It can accommodate 6 electrons. However, 2 electrons are occupied. That means 4 electrons are 4. I mean, still four electrons are available. Four electrons can be filled in this, right? So this is for individual silicon atoms. If I have an n number of silicon atoms, this is how configuration goes on. However, when we have a silicon crystals, that means the distance between two silicon atoms are very close. Distance between two silicon atoms are very close. So the band energy theory says that this is the interatomic distance, and this is the electron energy. This is an electron energy, right? So if I bring all the silicon atoms to a distance of crystal latex, to a distance of latex, right? To a distance to a A0. What happens is that this outermost shell having a 4 electrons, right? 2 in 2 plus 2 is 2 gets split into a 2 energy band. That is what we call as, valence bands, and this is called as a conduction bands. So this valence band is completely filled. Why? Because it has only 4 electrons, and this energy accommodates 4 electrons. That means N stands for number of silicon atoms, right? So if I have an N number of silicon atoms, so this energy level accommodate 4N electrons, and this also accommodates 4N states, right? 4N electrons. However, since the outermost shell has only 4 electrons available, if I have an N number of atoms, that means 4N electrons are available, this energy band remains completely filled. So this is what we call as 4N energy states, and then 4N electrons are available. So this is completely filled, and this is completely empty, right? So this is what we call as conduction bands. This is what we call as conduction bands, and this is what we call as valence bands. This is how it goes, right? So this energy is what we call this is energy gain, all right? This is what we call as energy gain, and this energy gain is what we call as a forbidden energy gains. This is what we call as energy gain, and this energy gain is what we call as forbidden energy gains, right? This is what we call as forbidden energy gains, right? So this is what. So now, if I have a silicon crystals, and what happens is that outermost shell of a silicon atoms or silicon crystal is split into a 2 energy band, and one is what we call as a valence band, which is completely filled, and another one is what we call as a conduction band, which is completely empty. Alright, so this is what we have, right? Again, one more diagram I would like to give you. This is our textbook diagram. This is textbook diagram. Again, I will repeat this. This is very important for remaining concept. This is what I have. Again I am repeating this, right? These are the inner shell. These all are the inner shell, right? Inner shell, no interaction take place, right? So these are outermost shells, right? So before I bring silicon atom into latex forms, or bring into a crystal latex distance, every silicon atoms hardly interact with each other. They hardly interact with each other. They are individual silicon atoms. So therefore, if I have an n number of silicon atoms, I say n number of silicon atoms. If I have n number of silicon atom, each n number of silicon atom has 2 electrons in S shells and 2 electrons in a P shells. Alright, so P shell accommodates 6 electrons. So still 4 electrons can be accommodated by P shell. Alright, P, right? So therefore now what happens is that, so P having a 6, so therefore number of vacancy is what we call as 4. So this is individual atom, right? This is what we call as an individual. That itself is an isolated atom. Isolated atom. How many isolated atoms are there? N isolated. So in this case there is no crystal formation take place. Now when I bring these to a crystal formations, alright, when it comes closer and closer, one silicon atom start interacting, electron of a silicon atom, one silicon atom start interacting with the neighboring silicon atoms, right? So region D is what we call as actual spacing in case of lattice space. What I mean is that this entire outermost shell gets split into two energy bands, and this is what we call as valence bands, which has a 4n state. N is the number of atoms, right? 4 is the number of available state, all right? And then 4n electrons. So that means this energy band is completely filled, and number of state is 4n state. However, no electrons are available, so this is completely empty. So this is what we call, and this is what we call as an energy gap and energy forbidden. That means energy forbidden means no electron can occupy this space. So forbidden band, right? So this is what we have, right? So in short, what we have to understand is, if I have a silicon atoms, and if I have a silicon latex or germanium latex, whatever latex may be, crystal latex, and the outermost outermost shell gets split into a two energy band. One is what we call as a valence bands, which is completely filled, and another band is what we call as a conduction band, which is completely empty. And the electrons which are available in the conduction bands can conduct electricities, and the electrons which are in the valence band does not conduct electricity. Valence band electrons are fixed. Valence electron bands are fixed. They cannot move from one point to another point. There is no flow of electron taking place in the valence bands. If the electrons are available in the conduction bands, then flow of electron is possible. So that you should keep in mind. This is true even for metal also. So this is again this is a crystal lattice space, which I told you many times. Atomic space, that is, if I have a crystal lattice space, what happens is that this is energy gate. This is the valence band. V stands for valence bands. For silicon, it is 4n, which is completely filled, and conduction band 4n state, but number of electron is going to be 0. 4n state, number of electron is 4n electron, 0 electrons. That is what we have. All right. And this is what we call as a forbidden energy gate. No electron, no electron can occupy or can stay in this energy gate. All right. So this is what we have. All right. Conduction band and valence band. Again, I am repeating. If electrons are not available in a conduction band, then we say that that particular material doesn't allow a current to flow. The electron in a valence band doesn't participate in a flow of current, in a flow of electrons, right? So this is what we have: valence bands, conduction bands. So this is what we have. Now what we would like to tell is, this is how we discuss, right? So this is how we write. So this is what we call as a field. This is what we call as a field. This is what we call as fields, conduction bands. For n, this is what we call as a conduction, or this is what we call the valence bands. This is what we call as a valence bands. and this is what we call as a conduction bands. And the valence band is completely filled, and the conduction band is valence band is empty, and conduction band is completely filled. A number of electrons available in a valence bands is what we call as 4n electrons. If I have 1 million silicon atom, 4 million electrons are filled, which are completely filled. 4 million states are available, and all the 4 million available states are occupied by electrons. So number of electrons available is this, and this has this many states are available, but no electrons are available at 0 Kelvin. Oh, this is okay. This is not okay. This is 0 Kelvin. 0 Kelvin, right? So this is what we have. Now, coming to this, yes. So let me have this. Look at here, right? This is for all the metals or the semiconductor or insulator, whatever. This is for semiconductor, right? This is for semiconductor like silicon, right? This is semiconductor for silicon, all right? Silicon, right? So silicon, how many states are available in a valence band? I say this is valence bands. How many states are available? 4 n states, all right? N stands for this. N stands for number of silicon atoms, all right? And this is the 4 n states. So this is completely filled. So therefore 4 n electrons are available in this band, and this is completely filled. I call this is a completely filled. This is what I call as completely filled, right? However, in case of conduction band, this is what we talk about conduction bands. Conduction band in case of silicon is how many states, right? 4 n states are available. 4 n states are available. However, number of electrons available are 0 electrons. 0 electrons are available. This is what we call as empty, right? Empty energy state, right? Empty, conduction bands, right? All right, and electrons which are available in the conduction bands are responsible for the flow of charge or electrons, right? And electrons which are available in a valence bands are the electrons which are available in a conduction valence band does not flow, right? Does not flow mean they are fixed. All right. So good conductor means so many electrons should be available. Bad conductor means no electrons are available, right? So this energy gap is what we call as forbidden energy gaps. This energy gap is what we call as a forbidden energy gap. So this is what I have. Now having this, now I would like to classifying a material based on energy band theory, right? So we have basically three, that is semiconductor, and then conductor, and then insulators. All right. So in case of conductor, we have two band diagrams. So that is one case is that electrons are available in a conduction band. This is what I call as a conduction band. Again, this is in case of conductors, overlapping of conduction bands, right? This is valence bands. Valence bands energy is higher than conduction energy bands, right? So that means the overlap. That means electrons are available in a conduction band, and the energy gap is almost zero. That is, energy gain is zero. All right, energy gain is zero. So this is one case. And in case of semiconductor, this is in case of semiconductors. In case of semiconductors, energy gain is less than 3 electron volt. Energy gain is less than 3 electron volts. So at 0 kelvins, number of electron in a conduction band is always 0. At 0 Kelvin, number of electron available in a conduction band is 0. So this is what we call as semiconductor. So that means the 3 electron volt energy is available, right? If I supply 3 electron volt energy, then electron can be jumped into conduction bands, so that electrons are available in a conduction bands. So semiconductor can conduct electricity. So therefore it is semi, right? Semi means conductivity is between conductor and insulator. In case of insulator, energy gain is more than 3 electron volt. So therefore it is very difficult for this kind of metal to conduct electricity. Why? Because so much energy is needed to excite electron from valence band to conduction bands. So much amount of energy is required to excite electron from valence band to conduction band. So this is how we classify metal based on energy band theory, right? So this is one more diagram I have. One more diagram I have is this. Insulator, conductor, and semiconductor and conductors. So these are the field. These are the inner energy level. These are the inner shell. I call it inner shell. Inner shell, right? So field, right? And now this is what we have: band, valence band, valence band, and valence band. In case of conductor, overlapped. All right. Valence band and conduction, they overlapped, and so that electrons are available in a conduction band even at 0 kelvins. In case of semiconductors, energy gain is very small. Energy gain is very small, so that 0 kelvin, at 0 kelvin no electrons are available. If at a room temperature, electrons are available in a conduction bands. And in case of insulator, energy gain is very big. Even at a room temperature, no electron can excite into conduction band. And this is how we classify material based on energy band theory. Alright, again I have this same. Alright, now what I would like to do is I would like to classify semiconductor into two parts. One is what we call as pure semiconductors. Another one is what we call as impure or doped semiconductors. Look at here. Pure semiconductor is what we call as silicon crystal, completely pure silicon crystals. So this is what we call as intrinsic semiconductors. And impure semiconductor is what we call the doped semiconductors. It is not exactly a pure silicon crystals, and some impurities are deliberately added, and this is what we call as extrinsic semiconductors. So first we will discuss what is pure semiconductors. And this is the silicon crystals, right? This is the silicon crystals. Basically, how silicon crystals are formed, right? Each silicon atom having 4 electrons, 4 valence electrons, and these 4 valence electron of individual silicon atoms starts sharing bond electron with the 4 neighboring silicon atoms and forming a strong covalent bond, right? This is how it goes, and this is a network. Silicon crystal networks. The bond is what we call as a covalent bonds, right? So this is silicon having a 4 outermost electron and binding, right, and sharing with the 4 other neighboring silicon atom and forming a strong covalent bond. And this is a silicon crystals, right? So the 3-dimensional diamond-like. This is a diamond-like crystal structure for carbon, silicon, or germanium with respective lattice spacing. That is, lattice spacing means distance between two silicon atoms, right? Distance between two silicon atoms, right? So 3.56, 5.43, and 5.66 angstrom. That is the distance between two silicon atoms, right? Silicon and germaniums, right? So this is what we have. So that means so every electron of silicon atoms are intact with its neighboring silicon atom, right? So this is what we at 0 Kelvin, then this conductivity is almost 0, and this is a two-dimensional diagram. This is a two-dimensional figures, right? Look at here. This is silicon. Let's say I say that this is the electrons of this particular silicons. Four silicon. Each silicon has four valence electrons, and combining or the sharing with the four other silicon crystals, right? Four other silicon atom, not crystal. I'm sorry. This is four other silicon, and forming a four covalent bonds. Right? Four covalent bonds, and this is what we have, right? So this is the network. All right. So this is what we have, and plus 4, plus 4, plus 4, plus 4, plus 4, plus. Why? Because this is excluding. Plus 4 indicates, this plus 4 implies that excluding 4 valence silicon atoms, right? If I remove four valence silicon atoms, then silicon has 4 axis positive charge. Therefore, we have written this as a plus 4, right? Plus 4, right? So plus 4, all are plus 4. And what happened is that now, this is valence at room temperatures. At room temperature, all right. Few electrons in the valence bands get excited into a conduction band, leaving behind a hole. This is a hole. This is what we call as a hole, and this is what we call as a hole. So now this space is available for another silicon, another electron to occupy. All right. And what happened is that now how many electrons are available in a conduction band? 2 electrons are available in a conduction band. All right. This is 1 electrons. This is another electrons. All right. This is in a lattice space. This is a lattice space, right? So 2 electrons, 1 electrons, and this is another electrons. This is another electrons, right? So this is what we have. So 4 electrons. These create a hole. This is what we call as a hole. All right. This is what we call as a hole in a valence band. So holes are available in the valence bands. Electrons are available in the conduction bands. That you should keep in mind. Very, very important, right? Holes are available in a conduction. Holes are available in a valence bands, and electrons are available in the conduction bands, right? So therefore, these are the valence electrons. These are the valence. So this is in a conduction. This is electron in a conduction electrons and hole valence. This is what we talk about. This is what we have. So for germaniums, look at here. I'm sorry, right? This is what we have. What is the energy gap? Energy gap is 1.11 electron volt. This is the energy valence band, and this is the conduction band. At room temperature, these energies are available, so few electrons jump into a conduction band. So in this case, how many electrons jump into a conduction band? 1 electron, 2 electron, and two electrons are free electrons are great, and 2 holes are great, right? 2 free electrons are great and 2 holes great in our conduction bands. Conduction band, 2 holes are great in a valence bands. That you should keep in mind. Alright. So this is so unlike metals, alright, when we talk about semiconductors, right, the flow of current is due to a hole as well as electrons. So there are the two kind of charge carrier, right? In case of a silicon, two charge carriers are available. Two charge carrier. So one is electron, that is electron in conduction band. Other one is hole in valence bands. That you should keep in mind. So this is the special about semiconductors. All right. This is energy gate. Again, I have the same. This is for germaniums. So this one is for. I'm sorry. This one is for silicon, right? This one is for silicons. This one is for silicon. So energy gate is 1.11 electron volt. Now I'll go for this is for germaniums. Same explanations. Only different is energy gate. So germanium energy gate is less than silicon. So how many free electrons are available? One free. This is the free electrons. This is the hole in conduction, hole in the valence bands. Free electron in conduction bands. Alright, so this is what we have. And energy gate is 0.72 electron volts. So this is completely filled and this is completely empty at 0 Kelvin. That you should keep in mind. So this is our textbook diagram. This is our textbook diagram. I told you what is y plus 4. That means if I exclude 4 valence electrons, so this is the, something like plus 4 inner positive charge, right? Why? Because I exclude 4 electrons. All right. So this is what we have, and this is a bond. This stands for bonding. That bond is a covalent bonds. So at 0 kelvins, this is what we have, right? Schematic two-dimensional representation of silicon or germanium structure showing a covalent bond at low temperatures. That means there is no electrons available, right? Now at room temperature, this is no electrons are available in a conduction band. So all electrons are in a valence bands. Now I'm sorry. Now I say at room temperatures, few electron can jump into a conduction bands. So therefore I call this as a thermally generated free electrons. Thermally means by a process of heating, right? So these create one hole in a conduction band and create one electron in create one hole in a valence band and create one electron in a conduction bands. All right. So what happens is that this electron can come and occupy this. So this is how the movement of a hole take place. This is how a movement of hole take place. So there is a flow of electron taking place in a conduction band. At the same time, there is a flow of hole taking place. All right. I write here flow of electron in conduction bands. All right. Then I say a flow of hole in valence bands. All right. This is how it goes, right? And this is side number 1 and side number 2 occupy this, and this is how it goes on, right? This is how. However, the movement of electron is opposite to the movement of hole. Why? Because one is positive charge, other one is negative charge. This is what I have, right? So this is using a band energy diagrams. At 0 Kelvin, this is at 0 Kelvin. At 0 kelvins, no electrons are available. This is at 0 Kelvin, right? This is at 0 kelvins, no electrons are available in a conduction bands, and there is no hole available in a valence band at 0 kelvins. At room temperature, 4 electrons get excited and jump into a conduction bands. At room temperature, let's say room temperatures. At room temperatures, 4 electrons get excited into a conduction bands, and 4 holes, right? 4 electrons in conduction bands. Conduction band, and 4 holes in valence bands. This is how. So therefore we see that pure semiconductor of no use, not much use. Why? Because pure semiconductors, number of electrons available in a conduction band is very less. Number of holes available in a valence band is very less. So therefore it is of no use, right? So therefore an intrinsic semiconductor at 0 kelvins behave like insulators, and at temperature more than 0 Kelvin, at room temperatures, electron hole pairs are available. Right? So therefore, in case of intrinsic semiconductors, number of hole, I write here, number of hole in valence bands equal to number of electron in conduction bands, and H is equal to an E. So this is in case of semiconductor, pure semiconductor. So therefore now what is the problem with pure semiconductor, right? Number of electron available is very less, and number of hole available in a valence band is very less. This is the problem with pure semiconductor. So now we have to design, right, such that number of hole in a valence band can be increased, and how to by what way we can increase number of hole in a conduction valence band, and by what way we can increase number of electron in a conduction band. And this is all done by extrinsic semiconductor by a process of doping. All right. So this I'm going to do in the next lesson. Thank you.